Okay, so as promised in the previous lecture, I will talk about some interpretations of the particle in a two-dimensional box, which we did last class, and also proceed a little bit more with the particle in the finite square well. Okay, so I will touch upon the two topics that we did last class. So, if you recall that the particle in a two-dimensional box, which has infinite barriers on all four sides, has a wave function which has two quantum numbers nx and ny. It just looks like a product of the wave functions of particle in a one-dimensional box. So it's just it looks exactly like a product, if you remember. The energy also looks like a sum of the energies in the two different directions. So what is the new thing that we get from this particle in two-dimensional box? So let us consider the following. So is there a way in which somehow two different wave functions can now have the same energy? It is likely because there are now two variables and you can have different combinations such that the sum is the same. Okay, so let us consider when this can happen. So if somehow nx squared plus a by a plus ny squared by b is equal to some other n prime x squared by a plus n prime y squared by b, where these numbers are different, then we will have two different wave functions and the same energy, right? So this is what is called degeneracy of wave functions. So they are distinct wave functions, but their energy is the same. So this is when we have a rectangular box and A is not equal to B. In that case, this is sort of an accidental degeneracy if there are numbers such that nx squared by a plus ny squared by b is equal to some other number squared by a plus some other number squared by b. Okay. On the other hand, if you have a square box, so if b is equal to a, okay, then there is a certain degeneracy. How is that? So if nx is not equal to ny, okay, then there is an obvious double degeneracy between any two distinct numbers. So if nx is equal to n1 and ny is equal to n2, which are two distinct numbers, not the same number, then this is certainly degenerate with another state where nx is equal to n2 and ny is equal to n1. Okay, so we have just flipped two quantum numbers between the x and y directions. And then these two states are definitely degenerate. And this exists for all pairs of values nx not equal to ny. Okay. However, if nx is equal to ny, then there is only one wave function, so there is no degeneracy in this case. So let us see an example of this double degeneracy. So let's take two values, two simple values, n1 equal to 2 and n2 equal to 1. Okay. So then we have two wave functions. Let's try to draw them. So if I have nx equal to 2, then in the x direction, I am drawing the one-dimensional wave function from what we have done before. So this is the wave function solution for the one-dimensional box in the x direction for n equal to 2. And for n equal to 1 in the y direction, you have this wave function where there is no node. So 0 node here, 1 node here. Okay. And the two-dimensional wave function will then be a superimposition of these two waves in the two directions. So this is just to guide me on how to draw this wave. Okay. because it's not easy to visualize a product of sine functions. Okay? So then what happens is, in this first half over here, you have the waves summing up. So you will have a peak over here, so a mountain over here. And in this second half, you will have a cancellation of the amplitudes from the y side by the x side partially, and you will have some sort of a valley here. So this is like a undulated wave over here. Okay, that is the two-dimensional wave function for nx equal to 2 and ny equal to 1. The corresponding density, however, will is mod psi squared, and this will have then 2 maxima. So this wave function has like one mountain and one valley, and the density has 2 peaks, 2 mountains. Okay. Now, if I flip the quantum numbers, if nx is now 1 and ny is then 2, then again you can draw the one-dimensional wave function in the y direction, the one-dimensional wave function in the x direction, and then the superimposition is again a similar kind of wave but rotated by 90 degrees. So over here you have the mountain and then you have the valley. Okay, so now we have 2 wave functions with the same energy. The wave functions also look qualitatively the same, they are just rotated by 90 degrees. So this is an indication of how degenerate wave functions arise. So even for p orbital functions, which you are probably familiar with, you have 3 degenerate p functions which are at 90 degrees to one another, roughly. Okay. So this is the simplest situation where a degeneracy can arise. Okay. So now that we have looked at an example of a wave function, how can we find the average position of a particle in a box? So this particle in a one-dimensional box, we have seen the probability distribution. So there's definitely some average value. So the place where you will most likely find the particle. So how to do that? So it's basically very simple. So the expectation value of any operator is given by an integral of the operator between psi star and psi, and you integrate over some volume element d tau. So if this is a one-dimensional wave function, then it is only dx, and if it is 2-dimensional, then dx dy. If it is 3-dimensional, then dx dy dz. Okay, this is the volume element, and you divide by the overlap integral, which is simply psi star psi. In most cases, we will have taken normalized wave function, so the denominator is simply 1 and you don't need to think about it. Okay. So now when the operator is x, then it doesn't do anything to the wave function. It is just a multiplication of x with the wave function. So for a one-dimensional box, the wave function is this, root of 2 by a sine pi x by a, and you multiply, and this is the real function, so psi star is simply the same thing, and you have x multiplied over here, and you simply have to evaluate this integral to find out the expectation value of x. And since this is a confined particle, you have a limit to this integral, so it's between 0 and a. And when you integrate this by parts, then you will get a by 2. And this is quite natural. Even intuitively, you would expect that for the ground state of the particle in a one-dimensional box, the maximum amplitude is at the center, and particle has is equally distributed across 0 to a. So the average position should be at the center of this box, which is at a by 2. Similarly, if you want to find the average value of the momentum operator, then you take the operator form of the momentum operator, use it on the wave function to the right, and evaluate the integral. Now what happens for a 2-dimensional box? For a two-dimensional box, like I said, d tau is dx dy. Okay, and since the wave function is product separable, then the double integral that we have, it separates into two separate integrals, one on x and one on y. Also, if you remember from the previous class, the x component and the y component of the wave function were individually normalized to 1. So this right integral has a value of 1, and you can integrate the first one only. That is the only one you need to do, and it is exactly the same as the one-dimensional case. So the expectation value of x, even for a two-dimensional box, is a by 2. And similarly, for the y direction, it is a by 2. So here we're talking about a square two-dimensional box, you see. So because you have a equal to b over here. Okay. So this completes our analysis of the particle in a one-dimensional box. You can, of course, do a lot of exercises using this simple wave function, and I can possibly give you an assignment with various things, which will with various exercises which will help to clear your concepts about wave functions in general, because this is a much simpler wave function in a model case. If you have like a hydrogen atom or something, the maths will always get more and more complicated. So it's better to understand everything with a simple wave function and then just extrapolate your knowledge afterwards. Okay, so I will probably give you something, but I haven't. But I will wait maybe a week or two, because you already have one assignment to do at the moment. Okay. Then the next thing that I was going to talk about is the particle in a finite square well. We found that there are two types of solutions for the finite square well. Even solutions, where the bound part of the wave function has a cos function, because for the even functions, because cos is an even function of x. And you have the odd solutions where you have the sine function. Okay. We are continuing only with even solutions, but you can of course do the same for the odd functions. It's just only because we need to do one of them, and the other can be simply done in the same way. We found that we arrived at an equation where there was a quantity called z, okay, that needed to be evaluated, and it was related to the quantum number L, which would tell me the energy of the system. Okay, so Z was defined as LA, where A is the width of the box, or the width of the well, and L is a quantum number, or well, not quite a quantum number, sorry. L is some sort of, it is a variable which will lead to the quantum number, let's say. Okay. So Z was defined as LA, and Z0 was some constant which is determined by the time properties of the problem. So by the depth of the potential well and the width of the well. And using these, and the equation which would tell me what Z is actually was this. So tan Z is equal to root over some constant square determined by the problem, and again Z square, which is the variable I want, minus 1. So this is what we wanted to solve. Okay. And the other relations that we had.
Ma'am?
Yeah?
I had a doubt. Can you go back up to the odd form of the wave function?
Yeah, sure.
Ma'am, how do we have f for both x greater than a and x less than minus a? I mean, shouldn't one be minus f? I didn't follow how it would be odd if they're both plus f.
You mean the
Coefficient? Yeah.
the well?
Yeah.
So you know the parts outside the well?
Yeah, the part outside the web.
Okay. So this part is so this basically we haven't determined k here. Okay. So actually, or kappa. So the values of kappa will also turn out to be different when we solve for the odd solutions. So then eventually it will turn out to be odd.
No, but what I was saying was, shouldn't we have minus f at for in one of the places
Oh, you mean
to make
minus?
it?
No, that is not necessary because again we will solve for f. So maybe it
Yeah,
turns
but
out to be some minus.
whatever f is, so if whatever f may be, if you have f for x greater than a, shouldn't you have minus f for x less than minus a? If it's an odd function.
Ma'am, what the final wave function is symmetric about 0, so we are maintaining the symmetry in both cases. If f is negative, then the symmetry of the wave function is not maintained in negative and positive direction.
Uh, yes, but we haven't determined f yet. So we don't need to. So you want me to have f, let's say positive for x greater than a and minus f for x less than minus a. That is what you would like, is it?
Yeah, that's what I thought.
No, because the sign of f here is not important. What you will be flipping for all solutions is basically the sign of x, right? So the f doesn't matter. You want me to have different f's on the two sides. Let me think about it. I'm not quite sure.
Okay, okay.
Yeah, I'm not quite sure. I have a feeling it will be fine even if we have both f's. But let's see. Let me work out the odd solutions and then I'll get back to you.
Okay, sure, yeah.
Uh, okay, so for the even solutions, okay, so these were the relations we had got before, that my z0 square over here is related to the two quantities k and l, and k is again related to the energy and l is also related to the energy. So we have basically a lot of relations over here. Okay, and we want to solve for z, which will tell me the allowed values of l and hence the allowed values of k and hence the allowed values of e. Okay, so this is our goal somehow. But this is a complicated model already, and it's not so easy to do it by hand exactly for a general situation. So we will just do some analysis of what happens in some limiting cases. Okay. So the points to be noted here are that Z0 is a dimensionless quantity and it is controlled by the problem. So Z0 is large when V0 is large and or when A is large. So it is something that tells me about the system. Then, and Z0 also tells me the number of possible bound states. Now, how can we say that? So let's look at this equation. So we have a left-hand side, which can be written as Z tan Z. So I have just modified this equation a little bit. Okay, so I've taken Z to the left, which is equal to root of Z0 square minus Z square. And let's say we call this function, so both left hand side and right hand side, equal to some function xi. Okay, so the idea now is that if we want to find solutions for z, we plot the left hand side and we plot the right hand side, and the points of intersection give me the solutions when left hand side is equal to right hand side. So let's try to plot the left hand side. So the left hand side basically looks like a tan z function, except when z is negative, and then it flips over here. But we are only interested in the positive side, so we will not try to plot anything for z negative. So for z positive, it looks more or less like a tan z curve, but it is a little. It is decay. Well, the asymptote moves to this y equal to pi by 2 line a little bit slower than the tan function. So a tan would go like more steeply towards this line. And if you multiply the z with it, then it goes a little bit slower. That's all the difference that you see if you actually plot it numerically, the z tan z function. Okay. And then again on the negative side, it continues to look like the tan function when z is positive. So there is basically not much difference. And if you look at this right hand side equal to xi function and you square it, then we get xi squared plus z squared equal to z0 squared. So this is the equation of a circle with the radius of z0. So we can plot that over here. And then I have the points of intersection which give me the allowed values of z. Okay. So the larger z0 is, the more solutions you will have, because the more number of z tan z plots this circle will cut. Okay. So it tells me that the larger the value of V0 and or A, the larger the number of bound states you will have. So a wide, deep well has more bound states. Also, the first, but since this z tan z plot passes through 0, any finite value of z0 will have at least one point of intersection. So you will have at least one even solution, which is a bound state. So for a finite well, there is at least one. However small this well may be, there is at least one bound state. Okay. It also tells us that, or in reverse of course, that if you have a narrow, shallow well, then you have fewer bound states. Okay. Now for the odd solutions, the solution turns out to be actually zeta equal to minus z cot z on the left hand side. So instead of tan, you have cot and you have a negative sign. Then the plots, they start at pi by 2 for the odd solutions. And it's again a similar situation with the cot plots. Okay. And then the Z0 circles are still there, the circles with radius Z0. But now for odd solutions, you see it is possible to have a small circle here which doesn't give me any bound solution. So this tells us that the even solution is the ground state. So it is the lowest. So you can always have an even solution, but you can have a potential well which does not give me an odd solution. Okay. So that's already time for your quiz. So I will not go on to scattering states now. Anyhow, you don't. So we will do this then next class. Okay. So I will just stop the recording now, and then.
Ma'am.